Right. Good afternoon, everyone. It's 4:05 p.m. sharp, and we'll go ahead and get started. This last technical session of today, I guess. This is the Homomorphic Encryption session part 2. I am Dr. Aydin Aysu. I'm an associate professor at North Carolina State, and we have 3 distinguished talks, 2 in person and 1 on Zoom, the last one, during this session. The first presentation will be given by Dr. Jiafeng Chi from Villanova University.
Okay, thank you. Thank you for the wonderful introduction. So my speaking is about CASA, compact and scalable accelerator for approximate homomorphic encryption. So unfortunately, my student cannot be here, but I will try my best to present it. All right, okay, so this is a brief introduction. Basically, as some of you know that it turned out to be that there are multiple generations of homomorphic encryptions available in the literature. And I think so far, according to our review, CKKS probably considered as one of the most promising FHE scheme, simply because of its operation, wide range, covers also the floating point arithmetic. So it can be applied in many practical applications. While the other schemes, for example, FV only covers the integer computation. So in this case, we mostly covers on the CKKS first. This will be our primary target in this paper. And I also talk about, a lot of times, to catch up for practical deployment, you just have to do with very fast calculation. In case that if the plain text processing speed is faster than the FHE computation speed, that's not good for practical application. So a lot of times we try our best to do the hardware implementation, and these are the available works for FHE accelerators in the literature, including FE, Great Lake, and BTS, and so on. The others ones FPG as well. So a little bit talking about the challenge. Most of the challenges comes from the computational complexity of the CKKS. The another aspect is the limited, we say that that's limited flexibility, because once the accelerator is fixed, it's very hard to adjust the processing kind of capability. And another one limitation we found out is actually the limited exploration on some of the key techniques. For example, most of the implementations are just based on the existing techniques with some slight modification or change the way how it should be calculated a little bit. All right, okay, so it comes to our paper. I think the first of all, of course, the details, you can read the paper, but one of the key innovation of the paper is on the arithmetic side. So compared with the traditional modular reduction technique, we kind of invented a technique called partially reduction-free technique. So it's kind of like we reduce the modular reduction to a certain extent, the cost. The second is we propose some very fine-tuned architecture that can be scalably accelerated or implemented. So we don't need to change the internal structure, it's generic. We can be scalably implement the accelerator on the FPG board. And the third aspect is the entity itself has, and also the overall structure on the architecture side is very much pipelined. All right, okay, so let's talk about the primitive function modules. So this is the target scheme we are targeting on. And concerning the first innovation, it's about the partial reduction-free technique. We want to emphasize, you can read the details is in algorithm 1 of this paper, but just give you some brief idea is because of the time limitation is that so CKKS provides a wide range of primes choices. So among all these primes, you can decide which one to choose. So in our technique, we decided to choose some specific primes that meets the requirement that, for example, of course, meets the requirement of CKKS, then meet the requirement that in a kind of trinomial kind of format, and also meets the requirement that it can be involve less ones, more zeros, and more importantly, it can be basically in the beginning part, it can be split into 2 parts through the Kalazuba, and then we discover that among these primes, we still have to do one type of small size Berkeley Montgomery kind of based reduction, and then eventually by the end we kind of use a similar technique with Kalazuba just to combine them together. So this gives us actually very much saving, because you can imagine that original is very large size, but end up with you only needed to do a very small size module reduction in the middle. The rest are just a shift and add kind of related operations. So this is one type of how we execute it because of the index. Index is, it determines by how many ones you are using for the coefficient. In this case, is very clear that we have just 3 ones, then the rest you just paddle them together and with some registers to increase the critical path. Then when this is just a small size kind of like a modular multiply, but when in terms of the whole partial reduction scheme, this kind of technique, you can look at the figure here. In the beginning part, we split them into 2 using the Kalazuba. Then through different stages there is one small Montgomery multiplication involved. But then after that, you have to, through different kind of combination, and then going through 2 still small, the shift sized, this kind of structure. And then eventually you produce the final result. Okay, then you have to cascade them, basically just connect them together to finalize it. This is the detail of how the final part is being kind of connected. This technique, I think, is novel to the field because of using this kind of technique. We are able to save a lot of resource usage in the final implementation, which you also can see later. And then the second innovation part is we design a very interesting NTT architecture. So this NTT architecture, there are ways to implement different kind of ways to implement the NTT architecture. But the way we implement it is that in the memory bank part, we set up a parameter called n subscript bf. So this n refers to the scalable kind of parameter. So as long as we put all the coefficient in these memory bank elements, and the whole entity can be operated in a way that it can be scalable, executed between different parameters. So as long as we don't need to change the memory access pattern, we don't need to change the other logic unit, as long as all the memory elements, they are stored there, pre-stored there, and plus this is in place entity architecture. So once the result is calculated, the final result will be in place in the respective memory banks or elements. And then we also needed to take care of dyadic and accumulation module. It's kind of like point-wise multiplication and the related accumulation, but it is still very important in the CKKS basic operations. As you can see that we have actually designed this architecture based on the previous proposed partially reduction-free multiplier, and then with a subtractor, and then with an adder, and also with a register to do the accumulation. And then from the lower part, there is the different types of data flow. It's just to calculate the whole procedure in a very nice way. The data flow is set in a perfect format, actually, especially related to the delta, negative delta to the power of negative inverse delta. Okay. So for the memory organization, this is a very one simple example here, that when we set up the memory in this kind of format, is that we try to, for example, according to our original setup, we could be within one port, we just set up the value just according to the sequence, but in our design is we try to set them according to the row sequence, actually. So in this case, the memory read and also write matches exactly what we want according to the scalable kind of format. So then apart from that, we also needed to design a modulus switching bank, because CKKS involves multiple modulus values. So between different kind of modulus values, you have to switch them. This is one of the example. It's mod down. The algorithm is shown up here. So anyway, the whole structure actually is shown up here. So the one why we designed this kind of format is it can be executed, multiple operations can be executed at the same time, meanwhile also take care of the pipelining and also take care of the scalability. So you can see that we use 2 muxes, okay, actually it's 4, 3 to 1 muxes to switch the memory banks. Then we have the dyadic and acceleration kind of component. We have the entity component, and also we have the modulus switching kind of component. These switchings are carried out in a very tightly connected format. For example, we just give you a very brief idea about how the scalable and the parallel computation is being executed. For example, in the original setup, could be mode up, mode down, and key switching. They could be 3 separate kind of events. But however, in our this kind of design, we set up in this kind of format. As you can see, different color represents, this is in total 9 stages of calculation, and then passing through a 12 cycle period. So the way we set up is that we use the time in a very efficient way. When one part, you can see here, there are muxes involved. For example, one part is like a memory bank 0 is executing, for example, say NTT, and then memory bank 1 is being prepared for next operation. So in this case, the whole pipeline is very much connected, and the timing is used in a very perfect format. So this is the overall implementation. So the implementation of ZCU FPGA evaluation board, we use the parameters according to the existing literature references. 3 parameters sets we used here, and in terms of the implementation results, because different structures or accelerators, they use different types of resource usages. So we kind of transfer all the resource usages into equivalent format, so that we can calculate the exact performance. So this is still related to the resource usage, air usage. As you can see that our design is a compact design, and this is the timing performance as well. The timing performance, we definitely is longer than the others, but you can consider the other parameters and everything together. Actually, the final area delay performance is better than the rest of the designs, okay? So this is one part of our kind of innovation is because we are targeting one side is compact design. We hope it can be not only be implemented on very large size FPGAs, but also on small size FPGAs as well. And also this design is scalable, so you can see that we select different numbers. It's still generically give us very nice results, okay? So then next step is Arctic 7. How about Arctic 7? Arctic 7 usually is considered as a resource kind of like a constrained FPGA device. It's not considered as a nice platform for fully homomorphic implementation or acceleration. But somehow this, the proposed accelerator can still be operated on Arctic 7 devices. This is, I think this is the first implementation in the literature. And as you can see that actually the resource usage is still not that large, even we select different kind of parameters. Of course, the frequency is relatively low, but it's not that low actually when you compare with some of the CPU and GPU implementations, especially you consider the actual cost. For example, how about the power delay product? Then you can see that actually the Arctic 7 is very cost-effective strategy compared with CPU and GPU acceleration. And furthermore, you consider about all these, throughput per watt, and throughput basically is every throughput, how much you need to spend the money there. And you can see that both designs on different kind of accelerators, they still achieve better performance than the others, okay? So we say that this is a compact accelerator, so it potentially can be used in many interesting applications. For example, small size, multi-party computation, or even smart vehicles, this kind of systems. And this is the conclusion. I think because of timing, I can basically finish here. So basically, we proposed the scalable architecture. We proposed reduction, kind of partially reduction-free technique, and we also get good result, a very compact, fine-tuned architecture accelerator. So some of the future works we may explore in here, and if you have any interesting things, welcome to ask us. Thank you so much.
We have time for a lot of questions.
Thanks for your talk.
Yes.
I have two questions.
Yes.
The first one is like, can you give a rough number of how many logic gates or flip-flop can be saved by using the proposed modular reduction unit compared to the conventional Montgomery reduction?
So this is a good question. I think because somehow our multiplier and also the Montgomery reduction techniques, we kind of like combine them together as a whole, as you can see here. So actually, we exactly how many gates can be saved, we haven't, accurately, measure it. But theoretically, we just kind of according to our kind of intuition, and then according to our theoretical analysis, we say this can save really a lot.
Okay, thank you.
Yeah.
My second question is that you mentioned the scalability of this design.
Yes.
But I have only seen like the largest degree of polynomial support in this slide is 2 to the power of 14, I think.
Yes.
So can you demonstrate a larger parameter set for like some tests like bootstrapping?
Yes. So this is a very good question, actually. First of all, I think, because our target is on targeting the small size, compact kind of accelerator. So by the time we, I think, developed this kind of scheme, actually the paper was done in early kind of like spring of 2023. So I think when we search all the existing literatures, we didn't find a very large parameters available. Kind of people are doing that at that time. So we just set our parameter according to the previous kind of designs at that time. But this will be an interesting exploration. We can definitely look into that. Yeah.
Thank you.
Yeah.
Thank you for your talk.
Thank you.
I have one question related to the partially reduction-free
Yes.
multiplier.
Yeah.
If I understand correctly, the RNS primes that used for this multiplier has some restrictions other than the conventional entity primes. So I'm wondering whether there are enough number of those special primes for this multiplier, and is it enough for having for instance, fully homomorphic encryption, like where we need like 10 to 20 or even 30 primes?
Yeah, very good question. Actually, during our kind of this kind of technique development, so we kind of like search all the possible prime numbers that fits in this range, and it gave us just exact the prime number according to the CKKS recommendation, just exactly the same. So this probably, on one side is say we are just kind of right there. We meet the requirement. We don't need to skip over. But on the other side, that strongly indicates that there is the future room that we can explore more on this kind of partial rate reduction kind of free, this kind of technique, so that we can have a more larger number of primes meet this kind of requirement. Yeah, very good question. Thank you.
Can I ask one more short question, maybe related to the question given by him?
Yeah.
You said that you use only the lattice dimension, ring dimension as n 2 to the 14, and you said that you have exactly the required number of primes,
Yes.
and
Yes.
it is for the 2 to the 14.
Yeah.
Then if we want to extend it to like 2 to the 15 or 16, actually many fully homomorphic encryption parameters are used.
Mm-hmm.
Are we out of the primes?
I think we haven't actually exactly, as I said, the work was done in early spring that time. I think according to the 3 parameters, we definitely meet the requirement, but we haven't looked at the larger parameter size.
Oh,
Yeah.
Thank you.
Yeah, thank you.
I have a quick question.
Yes.
Is your code open source, or do you plan to have it open source?
So far, it's not open source. Yeah. But if it will be open source or not, I need to talk with my student.
All right.
Yeah.
Sounds great.
Yeah.
Any other questions? Right, let's thank the speaker again.
Thank you.
So our next speaker is Ben-Chan Wei, and the paper is Thunderbird, Efficient Homomorphic Evaluation of Symmetric Ciphers in 3GPP by combining 2 modes of TF-HE.
Thanks for your introduction. It's my pleasure to be here to share our work, Thunderbird efficient homomorphic evaluation of symmetric ciphers in SandJPP by combining two methods of TFTE. My name is Ben Qianwei. This work was joined with Xianhui Lu, Ruida Wang, Kun Liu, Zhihao Li, and Kunpeng Wang. This presentation is divided into 3 parts. First, I want to give some backgrounds about homomorphic encryption. Homomorphic encryption involves the computation of arbitrary functions to be performed on encrypted data without decryption. So the client can send the cipher text encrypted by FTP to the server, and the server can perform some functions on encrypted data, and finally the client can receive the cipher text and decrypt it to get the final result. So now we have 3 popular FT schemes. The first one is BFAV scheme. The second one is FT-like scheme, and the third one is CHES. But now we have two problems about FT. FT now has a relatively slow efficiency compared to the plain-text computation. And the second problem is it has very large cipher size expansion. So an effective solution to solve the larger cipher text expansion is to use hybrid homomorphic encryption. Hybrid homomorphic encryption is also called transfer sharing. It can reduce the transmission communication cost between the client and the server by integrating symmetric encryption scheme. In HAD, the client, instead of using FT to encrypt data, it can use the symmetric cipher to encrypt the data and send the symmetric ciphers to the server. What the server needs to do is to convert the symmetric ciphers to the FT ciphers. Then he can do homomorphic operations. This slide shows the hybrid homomorphic encryption workflow based on block cipher AS. And actually, now hybrid homomorphic encryption workflow based on stream cipher, it is more preferable because the key generations of stream cipher can be offline. The encryption and the decryption process is only XOR operation. So now there are 2 directions about HAT. The first one is we can use well-established and standard ciphers like AS. The second one is now there are a lot of works to study about to design FT-friendly ciphers. FT-friendly ciphers, it has low multiplication complexity and low multiplication depth. But however, in this paper, our motivation is that this new FT-friendly cipher test, I think we have very low confidence in the security of these new ciphers, and they lack our long-term security like AS, and the road to standardization of these new ciphers is very long and very difficult to apply. So in this paper, we focus on standardized cipher test of SandJPP. It has 3 ciphers: Snow SandJ, Zook, and AS. So we propose the Thunderbird evaluation frameworks that can customize different evaluation strategy for different functions types of ciphers. First, this slide shows the Snow-Sanjay ciphers. Snow-Sanjay ciphers has initialized and key stream generation mode. As we can see, Snow-Sanjay consists of these three function types: bitwise XOR, modular identification, and lookup table. And this slide shows the Zook ciphers. It also consists of these three function types. So a very important question is to evaluate these ciphers is to how to choose a suitable FG scheme. A basic principle of FG scheme selection is that we must to consider message type, function type, and the depth of computation test. Now, these three populations, they have very different characteristics. And they can support different functions. For example, BJBFV, they support same packing and polynomial evaluations. And FG-like cipher test, now it supports efficient gate bootstrapping or functional bootstrapping or circuit bootstrapping. And as just we can see that Snow-Sanjay and Zook, the meta type is bit, byte, word, and the function type we have a modular addition, lookup table, bitwise XOR, bit shifting. If we want to evaluate this this four function types together, it is very difficult and very hard. So as we can see, so in this paper we chose TFT because TFT, I think TFT is more suitable. So this slide shows some backgrounds about TFT. The most important is that TFT, we have two different evaluation models. The first one is FT models. FT model means that if we evaluate a gate, we must perform bootstrapping. So this is very cost. The second one type is LHT mode. In LHT mode, that means we don't need bootstrapping after every gate because we use the CMAX gate. CMAX gate is that it is the internal multiplication of TRSW and TRLWE. So, so the first one, our evaluation strategy is that we use bitwise encryption. That means we can perform bit shifting free, and especially for the evaluation of modular addition, we proposed a single gate bootstrapping for address. You can find some details about in our paper. And the most point is that how to evaluate the 32 times 32-bit XPOS evaluations. Because nonlinear functions lookup table are heavily used in Snow-Sanjay, and the XPOS SB1 maps 32 bits input to 32 bits output, and also we use the mal alf and the del mal alf, they also maps 8 bits to 30 bits and are used in initialized model as K-stream models to opt the LRF. So SB1, SB2, mal alf, and del alf consists a lot of billion gate. So if we just use gate swapping, it will be very, very expensive. So our observation is that SB1, SB2, they can be implied some 8 to 32-bit tables, and mal alf and the del alf can be also implemented as a table lookup from the table. Mal alf and del alf, they are also 8 to 30 bits lookup table. So in this, we decided to replace a lot of billion circuits with lookup table to improve the whole computation efficiency. This slide shows how to evaluate the 8 to 30-bit lookup table. Actually, we, as just we said, we use CMAX gate and mix packing. Actually, this technique is from the original TFG paper. So, but we have a very big problem in this mode. That is, the input selected bit cipher is TRGSW, while the output bit cipher is TRW. So if you want to move the next one, that is incompatible. So we must use circuit bootstrapping. Circuit bootstrapping actually means it can convert TRW ciphertext to TRGSW ciphertext. So actually, it consists of 2 steps. The first step is PBS manual lookup table. Actually, it also called functional bootstrapping. And after this step is that we must to convert the TRW to TRLW. We can combine this TRW ciphertext to the desired TRGSW ciphertext. In this paper, we accelerated the second step because we can see from the picture that the first row of TRGSW, it is related to secret CHES. So we just to achieve this first rows of TRGSW actually the first rows of TRGSW can be constructed by operation that is called evaluate square mult. It is proposed by KLD 23. Actually, evaluate square mult is a very simple operation. It can be seen as a key switch. So this step is very fast. So now we can put it together. So we can do some git swapping friendly operations and use TRLW, and we can evaluate some locatable friendly operations to we can use LHT mode to evaluate locatable. So the next one is we find that we can apply this framework to AES evaluation. Now AES evaluation is very popular, and I think it has been evaluated by every FT scheme. The first line is based on BGV, and these 2 years it has been evaluated by FT like a scheme and CKKS scheme. So actually, AES can be implemented by using this for basic function sub-bias row shapes, mixed columns, and add around the key. This we in 2023 IS conference we just evaluated this for step. And actually, AES can be also used locatable based in locatable based implication. It merges sub-bias row shapes and mixed columns. These functions into 8 to 32 bits locatable. So we can use our proposed framework to AES. As we can see from these two boxes, in the green box, we evaluate all the functions of AES. Every step actually is very fast, but we need circuit bootstrapping to convert the cipher test type. It shows in the orange box. In the orange box, it is circuit bootstrapping. Actually, the circuit bootstrapping is our bottleneck in our AES evaluation framework. So these are the parameters, and these are some comparison of FTA-friendly stream ciphers. And these are our comparison of AES evaluations. As we can see from the table, now we can improve the efficiency of an AES block to 46 seconds. And our recent result is now published in Eurocrypt 2024. Because we, as just we said, the circuit bootstrapping is our bottleneck. So in this paper, we proposed faster and smaller circuit bootstrapping. I remember in the paper, it is maybe 26 seconds. Yeah. So this, so in this paper, we investigate the possibility of applying the standardized symmetric cipher in SandPP to hybrid homomorphic encryption, and we proposed the standard border evaluation, which combines the TFG level evaluation model and the bootstrapping model to address the different functions. So, yes, thank you.
Right. We have time for questions. No questions? All right, let me go ahead and ask the first question. Can you go back to your results? So here in this work, you are comparing yourself. I guess the closest comparison is to the LHE scheme, which is 86 seconds, while your first design is 10, and the second one is 46.
Yeah.
Right? So, and you mentioned there is a newer result that is even faster than this, right?
Yes.
In Eurocrypt. So, can you comment a little bit about how to maybe, like, is it possible to borrow some ideas from those other papers and then merge with your design? Or how do you see this getting even faster?
How to?
So I guess my question is about, like, what is the technique? Like, you propose a number of different techniques. So what is the most valuable optimization that you did that can potentially apply to these other previous works as well?
Yes, I think we can work. So I think our framework can be used in other scenarios. Yeah, such as maybe can use the tributable neural networks. Yeah.
Any other questions? So is this code open source, or do you plan to make it open source?
Yes. The Frigata has been open source, and our recent result in Eurocrypt 8 has been open source.
That's very good. So you win a pin for open source designs. Thank you.
Thank you so much.
So the final talk of this session will be an online. It will be presented by Ziyuan Leng.
Hello, everyone. My name is Yuan Liang, and I'm honored to present our work titled Shaper, a general architecture for privacy-preserving primitives in secure machine learning at CHES 2024. This work represents a collaborative effort between Zhejiang University and Alibaba Group. Today's presentation includes the following 4 parts as shown in the outline: a background and the motivation, the design of our Shaper architecture, implementation and the evaluation, and at last, a small summary and some future work discussion. To begin, let's talk about secure machine learning, or privacy-preserving machine learning, PPML. As machine learning models become increasingly integral to critical applications, from healthcare to finance, the need to protect sensitive data used in these models has never been more crucial. Traditional machine learning approaches often fail to consider privacy implications, leaving data vulnerable to exposure. In response to these challenges, privacy-preserving techniques have been developed. For example, SecureML in 2017 utilized 2 servers for training and inferences in secret sharing. Common private computing primitives include secure multi-party computation, homomorphic cryptography, differential privacy, and trusted execution environment. However, these schemes often come with trade-off in performance, complexity, and scalability. Existing PPML solutions are almost entirely impractical for industry. MPC-based PPML has high communication and is difficult to deploy on large, complex models, while HE-based PPML has high computation and needs targeted optimization of the model. So, is it possible to use different primitives in combination in order to mask each other's drawbacks? And some existing work has proposed to combine secret sharing and additive homomorphic encryption to utilize the special data characteristic in machine learning models. Note that the feature matrices in real-world scenarios are often sparse. For example, there might be some single-point functions, or there are some partially missing features in the real-world samples. If it is simply split into two shares, the data security can still be ensured, but the sparse vector will become two dense ones. Hence, the sparse feature of the data cannot be further leveraged to reduce the overhead of the solution. In CHES in 2021, they have applied homomorphic encryption to the sparse vector, and then multiply homomorphically, convert the result back to the shares, and finally output the share product. And that inspired our motivation of this work. Building PPML schemes with one primitive alone is far from the performance demands of real-world machine learning applications. Compared to the pure secret sharing-based PPML solutions, AHE and SS hybrid PPML can achieve a performance improvement of several tens of times. So is it possible to further optimize the performance, specifically for the hybrid primitive PPML? We optimize the performance in two aspects. The first one is hybrid hardware-software architecture, and the second one is cross-layer collaborative optimization strategies. And then I will introduce the design of our Shaper architecture. We have listed specific strategies in the overview. Shaper builds a software-hardware architecture, applied with cross-layer optimization with original and existing strategies to achieve performance improvement of PPML. The strategies listed in the table will be introduced later in detail. The overall architecture is divided into software side and the hardware side. The software and the hardware parser come up with the controller of the Shaper architecture. The host applications invoke hardware through instructions, and the parser generates hardware control flow based on the instructions sent from the host. The storage part of the Shaper architecture includes the onboard memory and the on-chip cache. The secret sharing unit consists of multiple integer processing engines and the cryptographic secure pseudo-random number generator, CSPRNG. The integer processing engines support computation over 64-bit integers, which is a common choice in secret sharing-based schemes. The CSPRNG generates the random numbers used in the secret sharing schemes. We use SHA-3 catch-up engine to generate randomnesses for better throughput. In addition, we also use a FIFO buffer to catch these generated random numbers. The AHE unit of the Shaper architecture consists of a player controller and several engines. The controller manipulates engines to compute the functions of the player crypto system with 3,000 key lengths in parallel. Each engine implements modular multiplication algorithm. To accelerate the modular exponentiation, a set of URAM and BRAMs are deployed to store the keys and some other pre-computed values. Designing algorithm for hardware is quite different from designing algorithm for software. On one hand, it has to reuse hardware units as much as possible to increase hardware resource utilization. On the other hand, the data dependencies need to be reduced to further improve the parallelization and shorten the data path. The algorithm in Shaper handles multiple bits in one iteration, and its data flow is designed in rounds. Moreover, we propose a quick reduction trick to further reduce latencies. Here is our algorithm. Our high-radix shift-sub algorithm deals with k bits in a single iteration, and each round consists of a multiply-accumulate phase. We call this phase C, and a shift-reduce phase. We call this phase phase A. And note that there is no data dependency between phase C and phase A, except the final round. We observe that the reductions in the algorithm have special constraints, since the dividend have limited lengths. Hence, we propose a quick reduction algorithm to deal with the special case of constrained dividend length. We assume that the length of the dividend is not more than delta bits longer than the divisor. The core idea is to estimate the quotient of the division without actually computing the big number reduction. Two strategies are used for the estimation, including the MSB shift and Barrett reduction. First, we have observed that although the remainder in the division equally depends on each bit of the two input numbers, while the quotient of the division almost depends on the most significant bits of the two input numbers. As a result, we can estimate the quotient with a small division between their most significant bits. In specific, using only delta at 2 bits of the divisor can constrain the final error of the quotient within 1. And with the help of MSB shift, we can quickly compute the quotient of the 3000-bit division with a quite small one. The small one only needs 160 bits. And we also use the well-known Barrett reduction to further convert the small division into multiplication with the consideration of the hardware implementation. And the Barrett reduction will bring another quotient error, which is still no more than 1. And at last, the algorithm will correct the errors during the estimation by a conditional subtraction. The engine can also be divided into two modules, for phase C and phase A, respectively. Phase C consists of a block multiplication module and an adder module for accumulation, which consists of a carry save adder and a ripple carry adder. Phase A contains a multiplier to compute the quotient, block multiplication modules, and an adder to compute the estimated remainder, and a conditional subtraction module for the final correction. The pipeline implementation of the engine has 5 stages for each iteration. Each stage takes 4 execution cycles. Since phase A has a longer data path than phase C, we divided the data path into 5 parts. Pipelining strategy used in our Shaper architecture significantly improved the throughput of our designed engines. From this page, I'm going to introduce some cross-layer optimization strategies used in our Shaper architecture. The first one is computation and communication overlapping. Since the secret sharing and the additive homomorphic encryption schemes have balanced overhead, overlapping computation and communication will bring more benefits. This picture shows an example of execution process. The AHE encryption is the most time-consuming operation in the example, and can hide other delays. Once the first encryption is complete, the second encryption and the transmission of the first ciphertext are performed in parallel in the pipeline flow. Next, the second optimization strategy used in our Shaper architecture is pair pre-computation. We observe that the ME in pair encryption is under fixed basis, depending on the same public keys. An optimization using this insight is to store all the ME results of short powers in the offline phase, and a large number ME in the online phase can be converted into multiple operations. Here is an example. In this example, the ME will turn to 2 with window size 1, and the number of further reduced to 1 with the window size equals 2. Note that as the window size increases, the online computation overhead decreases, but the memory occupation for the pre-computed table will increases. And the third optimization strategy used in our shaper architecture is plaintext packing. The conversion between homomorphic ciphers and secret shares can be optimized with the packing strategy. The Palair message space is too large for the values in the models, and decryption in Palair usually costs much more than encryption. Therefore, the space can be divided into smaller buckets. Since there are fewer ciphertexts to send and decrypt, both communication and computation can be reduced. Note that the bucket size needs to be carefully considered, since too small bucket size will lead to overflow, and the large bucket size causes waste of message space. And the next part is our implementation and evaluation. We implement the prototype of Shaper, Silicon 16 nanometer VU13P FPGA using the Silicon Vivado toolchain. The table shows the resource usage of the Shaper architecture. The maximum clock frequency is 285 million Hz by default. We also evaluate the latency and the throughput of the engine, compared with the state-of-the-art designs. Since it is unfair to discuss throughput without considering resources, these designs are evaluated based on the average throughput generated by each DSP. The hardware design shows advantages in both latencies and throughput compared to the other proposals. We also evaluate the performance of our Shaper architecture in real-world PPML applications using practical network settings with 40 Mbps network bandwidth and 40 millisecond latency. In the experiments, we chose logistic regression as the benchmark application. The sample size varies from 200,000 to 1 million, and the matrix is sparse, with the sparsity equals 0.02%. The results show that the Shaper performs 94 times faster than Quasar, executed on the CPU when both using 2048-bit Palair. And last, I will make a small summary and discuss some future directions. So here is a small summary of this work. Our Shaper architecture introduces a new PPML implementation, combining algorithmic invocation with hardware acceleration. The co-design methodology achieves a 94 times speed up in logistic regression tasks, bringing significant improvement to PPML performance. At the end of this talk is a small discussion of the potential future works. For example, we can expand the use cases by using other data characteristics in machine learning, besides the sparsity used in this work. And this can further improve the applicability in other machine learning models, such as CNN and Transformer. Moreover, since hardware is involved in this work, potential side-channel threats needs to be taken into consideration. and the PPML implementation can combine more optimizations of no privacy protected machine learning implementations. For example, is it possible for PPML to take advantage of existing AI parallelization strategies or utilizing GPU resources? Since there is still a huge gap between PPML and real-world machine learning applications, we need more explorations in these areas. And that's all I want to share in this presentation. Thanks for listening.
Let's thank the speaker. So Z1 is online. It's, I think, 4 a.m. in China. So let's ask some hard questions. Any questions from the crowd? Z1, if you can hear me, I don't know if you can.
Hello.
Ah, great. So let me ask you a question. So my question is about compilers. So how did you decide partitioning the algorithm into multi-party computation versus FHE parts? Did you do this manually, or did you use any automated systems or any compilers to help you explore that?
I think in this work we do this part manually. For example, we will put some linear layers. We'll do some linear layers by homomorphic encryption, and for some nonlinear layers, we will operate them in MPC. I think this is the I think this is our strategy to decide which part to do it in homomorphic encryption or MPC.
I see. So you, in your future works, you mentioned extensions to other types of machine learning algorithms. So I guess in that scenario, you had to redo that work all over manually, right?
Yeah, that compiler work we'll consider to put it in our future works.
All right, sounds great. Any other questions from the audience? And also, like, do you plan to open source this? Like, is there any GitHub links that we can use to check the code?
The only thing I can say is we have the plan for open source, but as you can see, this is a cooperative work between Zhejiang University and the Alibaba Group. So we cannot decide alone to about when to open source it.
Fair enough. Right. If there are no other questions, let's thank the speaker again.